Hi, I'm Lesley Vestal, and I'm doing my PhD in physics with Dr. Musalek, and I'm going to talk to you today about Null Lagrangians, a new tool to investigate underlying symmetries of the universe. So first, we should talk about what a Lagrangian is. So Lagrangians are this tool that's widely used in physics to characterize the energy of a system. You can apply them all over the place. So you can use them to talk about a ball rolling down a hill, or you could look at the energy of multiple particles in a particle collider, or you could look at a few different planets orbiting each other. We use them all over the place because they are so applicable and they describe the energy of the system. So what we do is we write out our Lagrangian to talk about the system, and then we feed it through this thing called the Euler-Lagrange equation. And you can see this in the first box in blue. So once you feed it through the Euler-Lagrange equation, it's going to spit out this thing that gives you information about the system, and we call that the equation of motion. So you might look at the equation of motion and determine the acceleration of an object, and it could tell you about that. So what I do is I add this thing called a Null Lagrangian. So Null Lagrangians have been very widely explored in the field of mathematics, and they're used for different applications in engineering. But in physics, we have very much ignored them, which I think is absolutely to our detriment. So I add this Null Lagrangian to the end of just a typical Lagrangian, and then I feed it through the Euler-Lagrange equation, and it's going to spit out the exact same thing. So it seems like the Null Lagrangian didn't even matter. It didn't change what we got out of the equation. That's why we call it null, because it just drops out. One more thing about the Null Lagrangian is that you can find the gauge function. So we call this thing the gauge function, and it's related such that if you take the total derivative of the gauge function, it's going to spit out the Null Lagrangian. And that's shown in the second box. And I'm going to tell you why those are so interesting, especially the Null Lagrangians, but they are interconnected. So I'm going to walk you through a quick example of an oscillator. So think of just a spring, or I like to think of a slinky, and show you kind of why these Null Lagrangians are actually so interesting and why they are the key to exploring physics from a different way, but they've been hiding in plain sight this whole time. So it's kind of a new window into these physical systems. So the undamped oscillator that we're going to talk about, I've just written out the equation at the top, and then of course you can add a Null Lagrangian, and it won't change those equations of motion. It doesn't really seem to make any contribution. So we just add our little Null Lagrangian. So I kind of have that as a sum. It's the second equation. We add those on the end to our Lagrangian, and then we're going to feed it through that Euler-Lagrange equation. It's going to spit out the same equation of motion as we would always expect. So then we look at the energy function. So these are just typical things we do all the time in mechanics. So we're going to feed our Lagrangian into the energy function. So we have the Null Lagrangian and our typical Lagrangian, feed it right into the energy function. And this is where the really cool thing happens. So the energy function spits out this additional term from the Null Lagrangian. So we thought the Null Lagrangian had no contribution, but actually it becomes this additional term in the energy function. This contribution is novel, and this is a really interesting thing and a new result out of this method. So we look at that term and we're like, okay, what are you? Why are you there? What are you doing? That term happens to be force. So here we have introduced force in a novel way, or more so, we have seen how force can arise from the energy function. So it's arising out of the physical system. And this is the first time in over 300 years that we've been able to see how force arises from a physical system in a new way. So Newton introduced forces by adding them in. And here we found a more elegant way to let force arise naturally from the physics. So that's why I have some flowers here to kind of show that this is a new, elegant, novel way to do the same thing. So then we asked, will this still work if the system's losing energy? So a dissipative system. And then our second paper, as I've cited, shows that yes, it does still hold. And this introduces a frequency shift. So that means that we can use this even if we're losing energy. And we're still showing a new way to introduce forces to the system. So this is something so interesting and a new way to look at physical phenomena by using Null Lagrangians, which have been hiding in plain sight for hundreds of years. These also have a connection so that we could use them in quantum mechanics or in quantum field theory. So here we're building a physical framework so we can start to investigate all sorts of underlying symmetries through this new window to look at the physical system by using this new tool of Null Lagrangians.